So a few years ago, a student of mine was talking to me, and he knew I was into biking, and says, "Hey, why don't you come out and visit our family store? It's out at the 67,000 block of Mound." And I looked at him like, "There's no way I'm going out to 31 in Mound. I live in Royal Oak." And he was shocked. He said, "Well, how'd you know that?" I said, "Well, I know there's a nice function relationship between the mile roads and the street addresses. And the way it works is this: if you take 2,000 times the mile road, add 5,000, you get the street address. Now, it works for your major north-south roads and actually some of your side streets as well. So roads like Telegraph, DeQuinder, Mound, etc., you can do that. So like at Woodward and 11 Mile, 2,000 times 11 is 22,000, plus 5,000 is 27,000. Okay, so Jack's Car Wash right over there is going to have an address just a little bit more north of that, 27,000. But that's not what he gave me. He just told me the address. And what I did was I applied what's called an inverse function. So the function does something, the inverse function does the opposite. You're going backwards. So what is that inverse function? And understanding the inverse function is the point of this handout. So let's go through this. So we're going to chop off the thousands part in this functional relationship and just do 2 times x plus 5 instead of 2,000 x plus 5,000. And let's look at a few possible scenarios. So if it went all the way down to 1 mile road, which would be like what, Warren Road, because Ford Road would be 0. The addresses would be in the 7,000 block. So I'm not sure that this scheme goes all the way that far south. 3 Mile Road would be what, up at 11, and 5 Mile Road would be up at 15. So let's plot these points here and see what we get. If you'd like to borrow a ruler, I've got some up here. So we get a point at 1 and 7, roughly here. 3 and 11, about here, and 5 and 15. We can draw ourselves a nice little line that represents the graph of this function. But our goal is to not understand just the function, but we want to understand some stuff about the inverses. Now the thing about the inverse is that it does the opposite of what the function does. So the inputs are different. What I want to input is not the mile road, I want to input the address. So if I have my inverse function here, and I input a 7, what do I want to get out? A 1. I want this mysterious function to give me a 1. If I put in 11, I want to get out a 3. And you can kind of see what's going on. You're interchanging the roles of x and y. They're switching. They're flip-flopping. Let's graph this one. So 7 and 1, 11 and 3, and 15 and 5. Okay. So let's see what that looks like. All right, not bad. So here's your function, y equals f of x, and here's the inverse. Now typically I like calling it g of x. I do that more for my algebra students because they're not really comfortable with the more formal notation, which is y equals f negative 1. That is the inverse of x. But that's what we have there. By the way, does anyone know the equation of this line here? Y equals x, yeah. It is a special case of y equals mx plus b. It's when m is 1 and b is 0. So this is the line y equals x. Now the reason I point that out is because these two functions are mirror images of each other around that line. And that's something that I'd like you to be comfortable with, is the idea that one is the reflection of the other around this line. There's actually several different conclusions that we can get here. So one of them is this, what happens to the domain and range here. Now, if we wanted to, if we were just limiting this to mile roads, this would probably come down here to a 5. This would do likewise. So this would be the point 0, 5. This would be the point 5 and 0. You could play around looking at the domain and the range of these. So let's do that. Let's start with the domain of f. Domain is which set of values, your x or the y? X values. So the domain of f, is going to be 0 to infinity, at least by our graph. I mean, there's some practical limits here, I'm sure, but let's take a look at the range. The range of f. The range is the y values, and it goes down to 5. So it's going to be 5 to infinity. What about if we switch things over to the inverse? The domain of f inverse. At what x value do things start? 5. So 5 to infinity. And the range will be 0 to infinity. So notice what happened in going from the function to the inverse. What happened between the domain and the range? They flipped. And that's kind of summarized here. The domain and the range flip-flop. Finally, and maybe we'll look at this when we start playing around with some other things. If you do one of the functions and then the other, you're going to get back to where you started. So for instance, if I did the function, if I did f of 11, and then I did the inverse function, it would take me back to where I started. And that's what's happening down here with this third thing. So that's kind of some background on inverse functions. Let's play with some in terms of actually finding some. In fact, let's start by finding the inverse function in this case so that you can amaze and impress your friends. Now this trick isn't as cool as it used to be because everyone's got Google Maps on their phone and stuff like that, but it used to be pretty cool. Let's figure out the inverse function. So we'll start up here. F of x is 2x plus 5. First thing you're going to do is replace f of x by y. Y equals 2x plus 5. And then the next step is to interchange x and y. So wherever there's an x, you write a y. Wherever there's a y, you write an x. Finally, we have to solve for y. So I'll move the 5 to the other side and then divide by 2. The last little piece is to replace that y by the new notation f inverse. So there's your inverse function. You can apply it down here, or going back to that example from earlier, the 67,000 block, 67 minus 5 is 62, divided by 2 is 31. So 31 mile road. All right, are you comfortable so far with what the inverse function is and how to find it? We're going to spend some time first on how to find it, and then we'll also start talking about this part of it. Let's pick it up with a problem from the book. I typically like to do the even numbered problems in the book. That way when you're at home and I'm not around, you'll have a problem that you can look at as an example. So if you're stuck on problem number 5, take a look back at what we did in class, problem number 4, and maybe you can get some help on that. Problem number 4 asks us to find the inverse for f of x equals 1 minus x cubed. Well, there's 4 steps. The first one, just simply replace f of x by y. What comes next? Switch x and y. Good. So x equals 1 minus y cubed. Now we need to solve for y. Personally, what I'm going to do is move things around a little bit just to make it a little bit easier. So I'm going to move the y cubed term over to the left and the x term over to the right. Why do you suppose I'm moving the y cubed term over to the left? Yeah, so it'll be positive. Yeah, I want to get that term positive. When it changes sides, it changes signs. So moving it to the left makes it positive. Moving the x to the right makes it negative. So y cubed equals 1 minus x. What's the last step here? Cube root. So if I take the cube root on both sides, cube root of y cubed, cube root of 1 minus x. On the left-hand side, I'll get some nice simplification. On the right-hand side, not so much, but that's all right. I do get f inverse is the cube root of 1 minus x. And that's your inverse function. Yay. All right. Are we okay with the mechanics of finding that inverse function? Let's take a look at the graph. What should I see when I look at the graph of the inverse function? Anyone? Yeah, mirror image around the line y equals x. Now let me introduce you to a really cool website. It's called Desmos. So DESMOS. It's free. It's really nice. It's handy, especially if you don't have a graphing calculator or your graphing calculator is just not reliable or handy. So we can type in a function, say y equals 1 minus x cubed, and we get a nice little graph. Let me kind of zoom in a little bit. And this is something that's kind of cool that you cannot do with your calculator. You can interchange x and y. Let's do x equals 1 minus y cubed. Now typically when you're working with your calculator, you have to have y solved for, right? There you go. Don't have to have y solved for with Desmos. And let me put in the line y equals x here just for giggles. You can see that these two are mirror images of each other around that line. You can see some points where they cross, but they're nice reflections of each other. So, nice. It's what we expected. Nice to see that it matches. Are we okay with example number 4? Yes? All right. Let's try some more. Let's look at problem number 6. So if you happen to have the book and you're following along, example 6 is on page 44. So let me go back to DocCam. I don't know what's going to happen on the video when you replay that. I'm not sure if it's going to show up what I had on the screen or not. We'll find out. Somebody tell me. I hope so. So f of x is 16 minus x squared for x greater than or equal to 0. Now that's a little restriction there, and we're going to have to understand why they make that restriction and what it's going to imply for the function. So let's take a look at its graph first. Let me see if I can't get that up here. So let me just power these down real quick. And we want y equals 16 minus x squared. And then if you use some little brackets here, you can restrict that for x greater than or equal to 0. What's that restriction going to do here for us? With that restriction, go ahead. Yeah, it's not going to put in any negative values of x. Basically, you're just getting half of this graph. If I didn't have that restriction there, y equals 16 minus x squared, I get the entire parabola. So that's the entire parabola. We're only going to get half. All right, so let's go through and find the inverse then. So similar stuff as before. Y equals 16 minus x squared. X equals 16 minus y squared. What's my little trick here? Switch. Yes, thank you. Switch x and y, or switch the sides. So y squared equals 16 minus x. Last step. Square root. Thank you. So y equals the square root of 16 minus x. Now, the way we've written it, if you just did the square root, you'd actually kind of be missing out on something. What's kind of missing there if we're ignoring this part up here? Is a plus or minus? Yeah, which is it's a pain, but there is that plus or minus. Now let's go back and take a look at things. If I don't look at those restrictions, if I just solve for the inverse, I'd have, let me just cut it off here. Let's do y squared equals 16 minus x. So I think it's pretty clear that you've got the function and its inverse. But does anyone notice anything regrettable about the inverse, unfortunate about the inverse? Yes. Yeah, well done. Yeah, so exactly. This doesn't pass the vertical line test, so it's not a function. And for mathematicians, that's a problem. We want functions to work with. We don't want things that aren't functions. But let's go back and think about the restrictions now. So let me close this off, put this back on. The restriction said that x had to be greater than or equal to 0. So that's going to put restrictions on our inverse. Because when we flip this around, it's not going to be as big of a problem. In fact, what you'll get is y equals the square root of 16 minus x as the inverse. That looks convincing. Does the inverse pass the vertical line test? Yes. And of course, we did a lot of work before we figured out that the inverse passes the vertical line test, didn't we? We had to find the inverse, graph it, etc. There's a shortcut to that, and we'll talk about that shortcut in a minute. But let's review domain and range here. Alex?
Would you leave it as the square root of 16 minus x, or would you want us to simplify further?
It's a great question. Can we simplify any further? Oh, yeah, good question. The answer is you can't do that. So let me go back to the doc cam. So the square root of a minus b does not equal the square root of a minus the square root of b. And I can give you a number example on that one. Suppose we had the square root of, say, I don't know, 169 minus 25. Let's compare that to the square root of 169 minus the square root of 25. All right, so this is really 144, square root of which is 12. How does that compare to 13 minus 5? Yeah, doesn't work. So unfortunately, you can't distribute a square root. So yeah, good question. I do like things simplified. I think I'm going to try and be reasonable about the extent to which we simplify things, but I do want them simplified. Let's look back at the domain and range here. So because we have this restriction, that actually puts a restriction here. And that's going to mean f negative 1 of x is really just going to be the positive root here. I don't want the negative root. So If you were charging along and you absent-mindedly forgot the plus or minus, in this problem, it actually works out that you'd be exactly right. What I want you to do is take a look at both of these functions. Let me see if I can't make that a little darker. If you hit the Tools button, hit Projector Mode, that makes it a little bit darker for you. Let's put a couple points here, 0, 16, and 16 and 0. What I want you to do is come up with the domain and range of each function. So the purple one is our original function, and the red one is the inverse function. And then what I want you to do is I want you to compare it to your neighbors. So make a friend, see how you compare. And as you do that, I'm going to walk around and start learning some names. If you'd be so kind as to tell me what your first name is or what nickname you'd like to be addressed as in this class, I'd be most appreciative. Oh, and here's something I'll do. Let's see, you know what? I guess I can't pause it. Sometimes when I pause it on my handwriting, then I'll write a little note. Paused. So if you're watching this online and you just want to fast forward, then you can fast forward until you see me unpause or take out the note. All right. All right, go ahead, chat each other up. Find out if you got the right answer. If not, then figure out why. But this is your chance to actually interact with other humans, so take advantage of it. Good. Okay, so let's check in on this. Want to figure out the domain and range for each of these. So we'll start with the function itself. So the x values start at what? 0, and they go up to infinity. So the domain is 0 to infinity. Domain of f. Oops, yeah, I gotta change screens. .cam. So domain is 0 to infinity, and the range. Well, the range is the y values. So the y values, what did they peak at? What was the maximum? 16. So all the way down to really negative infinity. So negative infinity to 16. Domain and range of f inverse. Do we really have to think about these two? No, they're just flip-flopping from what the domain and range were just a minute ago. So the domain and range are going to be negative infinity to 16 and from 0 to infinity. Beautiful. Let's take a look back and double check that, at least graphically speaking, that it matches. So yeah, the domain goes all the way up to 16. That's where it stops. So that's the right-hand endpoint. And then you've got the left-hand endpoint. It would be negative infinity.
Is there something on the website that'll tell us this? So like if we were to figure it out, we want to check it.
The only thing that the website Desmos will do is it would be the graphing part of it for you. Yeah. If you click on interesting points, they will show up like points of intersection and intercepts. They should show up. Okay. Anything else on number 6 here? Doing all right in that one? Now, our original function that we started out with, y equals x squared, if you were to try and find the inverse of that, well, Kenny pointed out that it's not really a function. There's kind of a shortcut to this to deciding whether or not something, when you find its inverse, will pass the vertical line test. And that is, right here, when you're looking at the function, does it pass the horizontal line test? So if a horizontal line intersects the graph more than once, then its inverse is going to fail the vertical line test. We can see that. So a horizontal line here is going to be equivalent to a vertical line here. So it's kind of a shortcut. Let's write down a note or two about the horizontal line test. So if any horizontal line passes through a graph at most once, the graph passes the HLT, which is the horizontal line test. Now there's something special about these functions. First of all, if something passes a horizontal line test, then we're going to call it a one-to-one function. So functions that pass the HLT are one-to-one functions. What that means is for every input, you get a unique output. That's not true with quadratic functions like y equals x squared. If you put in 3, 3 squared is 9. If you put in negative 3 squared is 9. You're getting the same output for different inputs. But with one-to-one functions, that's not true. It can't happen. Now, another thing special about functions that pass the HLT is that their inverse is also a one-to-one function. So the inverse of a one-to-one function is also a one-to-one function, or is also, let's see what it, yeah, necessarily would have to be a function. Also, it'd be a function or just a one-to-one function? I think it's going to have to be a one-to-one function. So the inverse at least is going to be a function, and I'm pretty sure that it's going to be a one-to-one function. Well, the one-to-one function is going to pass the vertical line test and the horizontal line test. It'll pass them both. Yeah. Let's take a look at a problem like number 16. F of x would be 6x over x squared plus 4. So let me graph that on Desmos. So y equals 6x over x squared plus 4. Okay, so what do you think? One-to-one function or no? Does it pass the horizontal line test? No, fails it. Fails the horizontal line test. So it's not a one-to-one function. It fails the HLT. Let's look at a different one. Problem number 48. And problem 48 is kind of interesting because they give us a little restriction here on things. So, is there any thoughts on problem number 18? We're okay with our conclusion there? Problem 48 asks us to consider f of x is the absolute value of x minus 2 for x less than or equal to 2. Well, does anyone remember, roughly speaking, what the shape of an absolute value looks like? Yeah, a V. Which way has this one been shifted? To the right or to the left? Yeah, to the right. To the right by 2. So you can look at its vertex. Should be 2 to the right of the origin. Let's see if we can't pull that one up. So y equals absolute values down here, x minus 2. All right, so shifted to the right by 2. As it stands, is this a one-to-one function? No. But there's a little restriction here. And that is that x is less than 2. So let's put that in. X is less than or equal to 2. Oops, 2, not w. There we go. Is that a one-to-one function now? Yes, that one is. So we should be able to find the inverse. If it is, find its inverse. Well, it is an inverse function, so let's see about finding its inverse. Let's talk about the definition of the absolute value real quick. Actually, you know what? Let's do it this way. Without getting mired in the definition of the absolute value, let's look at this function and understand a few things about it. Let's figure out the domain and the range for this. What's the domain? Yeah. All right. So, and we're moving from left to right. It'd be from negative infinity to 2. All right, 2 to negative infinity. Yeah, I understand what you're meaning there. So the domain is negative infinity to 2. What about the range? Good, from 0 to infinity. Is 0 going to get a closed bracket or an open bracket? Closed. Good, because we're including it. So, taking a quick look here, we got something like this. And that's just a little typo there. See if I can get rid of that. All right, well, let's try and figure out some stuff about the inverse then. What do we know about the inverse? Well, the inverse, we know what the domain and range is going to look like, right? So the domain should be 0 to infinity, and the range should be negative infinity to 2. Okay. Let's see if that helps us out a little bit. So switching back over to Desmos, what's the relationship between the graph of a function and the graph of its inverse? Mirror image over the line y equals x. So these 2 points are both actually going to be on the graph of our inverse. They're just going to be flipped around. In fact, they're going to land in their same spots. They're just going to switch. So what we're going to get is a line that passes through 0, 2, and through 2, 0. Except our line is going to start here and go on down towards negative infinity. So really what we want is the equation of a line that parallels this. So let's see if we can't figure out the equation of that line. So let's go back here. Okay. So we've got 2 points, 0, 2, and 2 and 0. If we're going to create an equation of a line in the form of y equals mx plus b, well, I already know what b is. B is 2. That's your y-intercept. The only thing I need then is the slope. So, quick reminder on the slope, y2 minus y1 over x2 minus x1. So that's going to be, we'll call this x2, y2. So 0 minus 2 over 2 minus 0. Yeah, 2 minus 0 would be negative 2 over 2 or negative 1. So we got our slope, we got our intercept. So it's y equals negative x plus 2. That's the equation of our line. But there's one tiny thing that we have to take care of. We have to make a restriction on this so that it satisfies the domain. If we were to look back at the graph, let me shut off this graph. Y equals minus x plus 2. That's everything. I need to make a little restriction. And that restriction should be that x has to be what? Yeah, it has to be greater than or equal to 0. X is greater than or equal to 0. And that's perfect. So there's my function, and here's its inverse. They kind of overlap here a little bit in the middle, but you got the function and its inverse. So nice. There's other ways to get it, but then you're going to get kind of stuck in dealing with the definition of the absolute value in a very formal sense. So this way is pretty good. So we got a nice function that passes the vertical line test, or the horizontal line test, and the vertical line test for that matter. Okay. Let's take a quick look at problem number 62, unless there's some follow-up on problem 48. It says determine an interval on the function, or determine an interval on which f is 1 to 1. So our function in problem 62 is f of x equals negative the square root of 25 minus x squared. Now, without taking out your calculators and graphing this, does anyone know what this graph would look like? Very good. Nice. It's a semicircle. Now, if you can't see that, let me help out a little bit. Let's replace this with y equals negative the square root of 25 minus x squared, and try and clean things up so that it's a little bit more obvious. If I square both sides of this relationship, I get y equals, or y squared equals 25 minus x squared. When you square it, that negative is going to disappear. And finally, let's put the negative x squared on the left-hand side and get x squared plus y squared equals 25. And here, this might be a little bit more familiar form. What do we have? We've got a circle. Where's the center of this circle? 0, 0. It's what makes the squared term 0. So center is at 0, 0. And the radius is the square root of this. Square root of that is 5. So that's our graph. Now when you actually solve for y here, technically you'll get a plus or minus. The positive root is going to be the upper half of the graph. The negative root is going to be the lower half of the graph. So this is the lower half of a circle or a semicircle. Beautiful. Let's draw that and see what we can do to make this a function, or a one-to-one function. So I'm going to cheat here. All right, so it looks more like a lemon than it does a circle. It's all right. Let's see here. Roughly speaking, so our graph is the lower part of this. It's just this right here. All right. Now this is clearly not a one-to-one function yet. But how could we make it a one-to-one function? What kind of restrictions could we do? There's two good choices. Yeah, restrict the domain. So what kind of restriction are we going to make from where to where? Yeah. Actually, we'll stop at 5, but yeah, you're right. Those other ones would work as well. So if you restrict it between, say, the domain between 0 and 5, or 0 and infinity would work too, then all of a sudden you've got a nice one-to-one function. Cool. Or you could restrict it between -5 and 0, and that would work. Now if we did this restriction right here between 0 and 5, so this point would be 0, -5, see if you could draw the inverse of this function. What would the inverse be? Try and draw that, and then check your graph against mine. So we've got a very distinguished gentleman here. His name is Hamza. And the cool thing about Hamza is he's got psychic powers. So he's going to concentrate on the inverse function. And ready, 1, 2, 3. Beautiful. All right, well done. So here's your inverse function right there. It's a mirror image around the line y equals x of our function. So well done, Hamza. Thank you. You can double check these in terms of domain and range. Your function has a domain of 0 to 5 and a range of -5 to 0, and the inverse function is just the opposite of that. So cool. Any wrap-up thoughts on inverse functions? Anything or facet about them that's a little bit unclear here? For homework, try 1.5. Sorry, this is section 1.5. Try 1 through 39. Now this is atypical. I usually don't sign the even problems. So 44, that's a little unusual. 45, 51 through 55, 71, 87 through 91, and 101 through 105. Well, that sounds like a lot, so we'll just make those the odd problems, okay? That way it cuts it in half for you. So it's not so bad. Yes, sir.
I have this book right here. Does that like correspond with problems?
There should be some good correspondence. I don't know exactly what it is.